Good morning, good afternoon, good evening, everyone. Thanks a lot for joining me today. Also, I would like to thank the organizers of the event for the kind invitation for me to share some of the new insights into neutral salts activation of blast furnace slag cements. I'm Professor Susan Bernal Lopez, a professor of structural materials in the School of Civil Engineering at the University of Leeds in the United Kingdom. So, as many of you are aware, we are suffering a climate emergency at the moment, and the construction sector in general is taking a lot of different measures to try to contribute to decarbonize their practices. So when we think about decarbonization strategies, we need to think about the different scales that involve the construction sector. For example, what environmental footprint of a given structure could be different or could be enhanced. For example, if we think about the building level, or if we think about concrete level, or if we think about the cement level. So it's really important to think that every little counts, and we cannot divorce the strategies that we will adopt for one particular item, for example, from the materials point of view as cement and concrete, and how we use these materials when we actually create something new with them. For this particular talk, I'm going just to focus on the decarbonization strategies that have been developed for cement and concrete. The reason why is because there have been tremendous efforts in developing different what we call like research roadmaps or decarbonization roadmaps that are giving us like a guideline of the different things that could be done in the next 10, 20 years to achieve net zero in the construction sector, but particularly in cement and concrete production. So here I'm just showing in this table what is like widely commercially available. So strategies that have a technology readiness that is just there, like a hanging fruit that just can be adopted quickly to generate change. Other technologies are not so widely commercially available or not at the technology readiness for us to use them immediately or in the next 5 years, but still with great promise to reduce the CO2 emissions of the cement concrete sector. So what is really interesting to see here is that some of these strategies, for example, clinker replacement, alternative fuels, optimization of concrete mix design, are already being adopted widely, but we recognize that even though we already apply these strategies, it is not enough to achieve net zero. So we need to be a little bit more aggressive in terms of what we really want to achieve. What is really interesting to see here is that in the cement concrete decarbonization roadmaps, alternative cements, including alkali-activated cement, are considered to a very low technology readiness, which I must say I disagree. Another thing is that they are considered like low priority, which I also disagree. Why? Because we have many different resources that nowadays are considered waste that could be used as precursors, as feedstock, or raw materials to develop these alternative cements. So it's like killing two birds with one stone. It's not just about creating new replacements of cements to compete with Portland cement. It's using the chemistry of these alternative cements to generate new routes that will enable us to gain some value of a lot of waste resources. When we talk about low carbon cements, I have to say I've been present in a lot of conversations about what a low carbon cement actually means. So at the moment, it doesn't seem to be a real consensus or a baseline that tells us this is a low carbon cement. For the purpose of this particular talk, I'm going to assume that low carbon cements are those whose production is associated with a lower embodied CO2 compared with Poland cement systems. So if we think about that, there are many different types of cement chemistries that will fulfill that criteria of the common cement. So one of the biggest families, I will say, is alkali-activated materials, also referred to as inorganic polymers or geopolymers, depending on the chemical compositions of the precursors used for their production, because of course they present certain microstructural differences. So when we think about this relative CO2 equivalent release in different cement chemistries at the production level, we can see in this graphic some of the most promising alternatives. So one is the Solidia cement, for example, that is using CO2 as a precursor to trigger reactions to create these new binders. But also we have alkali-activated materials. So the CO2 savings that can be achieved with this material can go between 40 to 80% compared with Poland cement. But this is dependent, of course, in the formulation of the cement we produce, the curing conditions, and many other factors during the manufacturing process. But still, it's very promising the CO2 savings these materials can offer. It is always thought that alkali-activated materials, and particularly considering the information in the research roadmaps for decarbonization, that the technology readiness is relatively low. And one of the reasons why I disagree is, for example, here in the UK, we have actually a standard that enable us to use alkali-activated cement in non-structural applications. Also in the UK, we have the Association of Alkali-Activated Cement Materials, which is testament of the increased number of startups and companies that wish to use this material at industrial scale. Also, we have a number of on-site applications that I would like to share. So for example, here, sorry, if this was a video, unfortunately it's not working at the moment, where I was showing the casting of some alkali-activated cement in London. So you can actually watch the video in the link that I'm providing here in the talk. But also, as mentioned before, there is a growing number of companies that are commercializing alkali-activated concretes at large scale across Australia, the United Kingdom, and Europe. So these are just some of the examples of the products that we can now find in the market and the companies that commercialize. But they are not just small companies. We're talking now about Cemex, for example, with the Bertura Ultra Cement, DB Group, Wagner, and so on and so forth. So I really question that comment that the technology readiness of these materials is so low that they are considered like a low priority in decarbonization strategies in different roadmaps. But what are alkali-activated materials? So perhaps I'm preaching to the converter, but for some of you, this is new. So alkali activation process is just a chemical reaction where we have a precursor or solid, often with an aluminosilicate type chemistry. Also can have some calcium present in there. And the typical way to produce this cement is having this precursor in a powdered form, mixing it with a source of alkalis on an activator, often in a liquid form, and then we produce these synthetic rocks. Also, there have been tremendous progresses in different routes to produce alkali-activated materials, also called just one part alkali-activated cements or one part geopolymers. But what is happening is that the precursor, solid precursor, is blended with the solid activator. And generally, you just have a powder you mix with water that triggers then all the reactions, similar to what we see in a Poland cement. But these materials, although they present tremendous advantages in terms of valorization of waste materials, also they develop compressive strengths similar to those of Poland cement, high resistance, for example, to fire, high resistance to acid attack, extremely outstanding chloride permeability resistance. There are some barriers limiting their uptake. So one of them, the principal restrictions is actually the availability of raw materials. Conventionally, alkali-activated cements have been produced with supplementary cementitious materials that are already used as cement replacements by the construction sector. So these are materials that are in tremendously high demand. For example, blast furnace slag, fly ashes, metakaolin. But again, as I mentioned before, there's so many opportunities to use resources from different processes to produce these materials. For example, metallurgical slags that might not be suitable as SEMs to production of blended cements. We also have ashes from agricultural processes. We have also low purity fly ashes from co-combustion with biomass that might not be suitable, again, as SEMs, but are very good for producing alkali-activated cements. So we need to be more open-minded when thinking about these. Of course, again, one of the main criticisms is like, well, we don't have enough like supply of these potential precursors to make the technology worthwhile. But once again, we need to think about the trade-off between using the right material for the right application and the opportunities for waste management that this technology actually offers. So it's not just about producing an excellent cement, it's also minimizing the amount of waste that are going to go to landfill or disposed of in different ways, and instead creating valuable products. So another barrier that has been identified for alkali-activated materials is the requirement of skilled personnel. Of course, alkali-activated materials, unfortunately, are not as robust as Poland cement in terms like we need to dose the binders carefully, also because we're handling corrosive substances, all the health and safety precautions need to be in place, and we really need to know what we're doing to make sure that we produce the products with the type of properties that we're looking for. So education will be absolutely key for people to use these sort of materials. But once again, it could be restricted the use up to a certain extent to precasting until we can overcome that skills personal requirement barrier. Again, it's not rocket science. We can train people to use these materials in a safe way to make sure that they are used properly and we can obtain the properties that we're looking for in the end product. Finally, it's always been said that the long-term performance of alkali-activated materials is unknown. I have been hearing that for over the past 15 years. And we already have structures with more than 100 years that are made of this type of cements and still standing. And many studies have come up in recent years demonstrating that these materials are very stable and are still durable when exposed to very harsh conditions. So perhaps what we need to do is just look at the evidence available and perhaps stop discussing so much about things that are not actually true, entirely true. So I invite people actually to look to some of the recent literature demonstrating the long-term performance of these materials in service. The other thing is, when we think about alkali-activated cements, yes, they can offer environmental savings between 40–80%, but actually the most pollutant component of this type of materials is the activator. So over the past, I will say 30, 40 years, a lot of attention has been paid mostly to find the precursors of the raw materials to produce this. Less attention has been paid to the activator. So here I'm just listing some of the conventional precursors that have been studied in the past, like a blast furnace slag, fly ashes, calcined clays, natural pozzolan. As you can see in this table, most of the research has been done using hydroxide or silicate activators. Less research has been done in using sodium carbonate activators, and almost no research has been done in using sodium sulfate activators. The reasons for that is because some of these less conventional activators, like the neutral salts, carbonate sulfates, they do not develop the same pH that compared with hydroxide or silicate activators. So some of the studies were not very successful. The materials didn't harden as quickly as they would like to, and therefore somehow that line of research was abandoned for a very long time. So I always wonder, well, in some applications, the sodium sulfate and sodium carbonate were actually very successful, particularly in the concretes that were produced in Ukraine for railway sleepers. So I started becoming quite interested in looking at the role of the activator in all these systems. And as we mentioned here, we can have hydroxyl groups or carbonates or sulfates or silicates in the system. And the activator will affect different properties in the material depending on the nature, depending on how much we put in the system, and of course, depending on the dissolution rate. So is it in a solid or liquid state? But when we think about it, the activator has 2 or 3 functions mainly. One is, of course, controlling the pH, because the alkalinity on the system will control how fast or how slow different species will dissolve from the precursors, but also the functional group in the activator, like sulfates, carbonates, or silicates, will react with these different species that will be in the post solution of once they dissolve to form new reaction products. So in other words, it's not just about a pH or alkalinity situation here. It's also how these different species interact with the functional groups in the activator. So overall, we'll say that the activator will control reaction kinetics, type and amount of reaction products forming, and consequently the microscopic properties. So it makes absolute sense to start looking and developing more research in terms of potential new activators for producing these cements. So here is just a brief overview of some of the factors that will control the phase assemblage, or the type and amount of reaction products that we will see in alkali-activated materials. So here we will see that when we have sodium silicate or sodium carbonate or sodium sulfate activators, depending on the content of magnesium present in the blast furnace slag that we can use, we have identified different types of secondary reaction products. So for example, if we use silicates and we have a high content of magnesium oxide, we have identified layer double hydroxides like hydrotalcite. But if we have low contents of magnesium oxide, we can form instead AFM type phases or zeolites. When we use, for example, sodium sulfate, we have identified that we can also form some layer double hydroxides when we have ultra high magnesium contents in the slags. But when we don't, we often see some ettringite and in some cases even formation of gypsum. What this means is that not all activators will act in the same way for all slag compositions. So what we need to do is actually identify those ranges in composition of activator and slag so we can select the most efficient activator for a given slag chemistry. And of course, depending on that and what the application of the final product will be, develop a tailor-made and really bespoke material. So imagine the opportunities to create concrete cements with many different properties using a single slag resource, but just varying the activation conditions that are being adopted. So for this particular study, I will focus my talk on sodium sulfate activated slag cements. And the main reason is because these systems have not been explored very much in the literature. And I found them really fascinating, if I'm honest, because when we think about sodium sulfate, first it's abundant and naturally occurring, which means that can help us to overcome some of the challenges in terms of CO2 savings in alkali-activated systems. We can reduce the global warming potential of alkali-activated cements if we make it work. Also, because the solutions of sodium sulfate actually achieve a near neutral pH around 7, we reduce the hazards associated with storage and handling of corrosion substances, which is the case when we use sodium hydroxide or sodium silicate. And of course, because it's not just naturally abundant, but also it can be produced as a waste of different processes, there might be opportunity to reduce the production cost of alkali-activated cement, making it even more attractive from a commercial point of view. Also, when we study sodium sulfate activated slag cements, the knowledge that we gain between the interactions of these sulfate and slag, for example, is helping us to understand other cement systems that are far more complex. For example, hybrid alkaline cements, which are gaining a lot of attention at the moment. And they're pretty much a blend between very small amounts of Portland cement, high amounts of supplementary cementitious materials, often fly ash or slag, and a little bit of sodium sulfate. But also understanding supersulfated cements, historically produced with gypsum as the sulfate source, but we could potentially use sodium sulfate. So from a scientific point of view, I found really interesting this particular chemistry. So just sharing with all of you some of the results that we have reported over the years in these systems. So in this study, we have slags from 3 different locations all over the world. The aluminum contents in the slag changed a little bit. So as the magnesium oxide increased, the aluminum oxide content decreased. But what is really interesting here to see from these isothermal calorimetry results is how when we use sodium sulfate, as the content of magnesium oxide increases, the material reacts faster. This is the opposite to what we have seen when we use sodium silicate, sodium hydroxide activators, when we see that if our slags are very rich in magnesium, they are almost unreactive when we use those type of activators. So this sort of behavior is conversely to everything we have known before for the alkali-activated cements. Similar results have been reported when we use sodium carbonate activator, which means that the absence of silicate or hydroxyl species in the activator is modifying the mechanism of reaction in these sort of systems. But then what is really interesting is, yes, we can see tremendous changes in the reaction kinetics when we change the slag composition and use sodium sulfate activator. However, the degree of reaction that these cements can achieve after a given time is more or less comparable, which means that we can produce, in theory, cement and concrete with desirable performance. But what we really need to do is understand and control the reaction kinetics during the first days of life of this type of cements. This is an XRD after 28 days of curing, and it's a very interesting one because when we examine the type of reaction products forming in sodium sulfate activated slag cements, we identified that when we have very small contents of magnesium oxide, but very high contents of aluminum oxide in the slag, we see formation of AFM phases along with formation of ettringite, which never has identified before for these type of systems. And it makes kind of sense because we have like an excess of aluminum in the system that is nowhere to react with. But then as the magnesium oxide content increases and the aluminum content decreases in the system, we just only observed as the secondary reaction product formation of ettringite, which is what has been often reported in different publications for this particular system. Most importantly is for the slag with very high content of magnesium, but very low content of aluminum, we couldn't see formation of crystalline ettringite, which was very unusual and very unexpected because we are wondering what happened with the sulfates in the system if it's not going towards formation of that. We can see in this diffractogram actually that we know forming like a lot of crystalline reaction products in that particular system. So it's quite amorphous, the structure that it presents. So because XRD might not have the resolution that we need to detect different types of reaction products forming, we conducted 27 aluminum mass, NMR spectroscopy in these samples. Also, these are some results, 28 days, to see if we could perhaps identify what was going on, particularly in terms of the secondary reaction products. So when we look at this NMR, we can see clearly the peaks associated with formation of ettringite consistent with the XRD results. We can also see the peaks associated with the later double hydroxide formation, and also the peaks associated with the aluminum binding in the catch phase. What's really interesting here to see is that in the case of the very high content magnesium oxide binder, we seem to be forming as some sort of layer double hydroxide, like that's the predominant secondary phase. But of course, as it wasn't identified by XRD, is very polycrystalline, which also makes sense with some recent results published characterizing the effect of the groups present in layer double hydroxides. So this gives us confidence that what's happening is that in the absence of aluminum, we kind of favor information of that phase. So in most recent studies, we try to evaluate then the effect of the aluminum oxide, leaving the content of magnesium more or less constant. These are commercial slags, so it was difficult for us to get all the variables in place. But what's really important to see here is that we can see significant difference in reaction with the slight changes in the composition of slag. So if we go from 11 to 9 weight percentage of aluminum oxide, we have a significant increase in the induction period identified by isothermal calorimetry. In this particular study, we also wanted to evaluate the effect of partially substituting blast furnace slag by limestone. The main reason being that at the moment, there is an increasing interest to reduce the fraction of blast furnace slag, because particularly in the UK and Europe, it is in very high demand, so low supply. So we're looking at composite type binders. So in these systems also, we see that when we substitute partially the blast furnace slag with limestone, we see a slight increase in the kinetics of reaction. So the material reacting faster, and we elucidate that this might be due to a nucleation effect, like a filler effect, rather than the limestone reacting in the system. So when we evaluated these materials up to 1 year using different techniques, and these are the XRD results, we couldn't see significant differences in the phase assemblage. In these particular systems that more or less have 6% of magnesium oxide, which is very typical for European blast furnace slags, the only secondary reaction product that we could detect was ettringite. in these systems, even with a moderately high or low aluminum oxide content, we couldn't see the formation of layer double hydroxides, which indicates once again why we need very extreme changes in the composition of slags to see the variation in the reaction products that we report in the initial study. Once again, we use a higher resolution technique to see we were missing something. And these are the aluminum mass NMR of the binders that we were evaluating here. And we can see that perhaps, although in a very tiny amount, some layer double hydroxide is actually forming in the system. And that was identified by this technique. However, that will be very difficult to detect by XRD. But overall, we can see that independently of the slag use, independently of the curing age, ethylene is the predominant secondary reaction product forming these materials. So we were wondering, okay, so will the difference in a slag composition affect perhaps the properties of the cache phase? And here I'm just showing an illustration of the structure of a cache phase expecting an alkali-activated material. So to make a little bit of sense of the results, I'm going to present in the next slide. So here we can see the silicon mass NMR for the two different slags at different curing times and also with different levels of substitution of limestone. And what we can identify here is that also there is no difference in the structure of the cache phase, because we see the Q21 aluminum, which is the cross-linking side in both. We see Q2 sides for both types of slags. But also most importantly is we don't identify any Q3s or Q4 sites for any of these slags, which means that the structure of the cache phases forming in the systems is more similar to that we identified in blended Portland cements compared to those that we identify when we use, for example, sodium silicate activators and we use in blast furnace slag. So the cache phases forming here are very similar to what we expect in a blended Portland cement system. When we think about the compressive strength, it's interesting to see that the chemistry of the slag actually has a strong influence in the properties. Again, these materials develop mechanical strengths of up to 32 megapascals, which is not bad for 28 days. And also when we look at the intrusion porosimetry, we see, of course, that the materials have different like pore size distributions and different sort of refinement. What is interesting here is that of course the sample that was produced with the slag with the highest content of aluminum oxide presented the highest porosity, which makes absolute sense. But it's really important to mention that more studies about the post-structural evolution of these sort of systems and perhaps tortuosity and how that might impact durability need to be conducted. So just to give you a little bit of a flavor on terms of carbonation performance, it's always said that alkali-activated cements are more susceptible to carbonation Portland cement, which is true. However, recent studies have demonstrated that the carbonation rates of alkali-activated cement and concrete are comparable to modern Portland blended cement systems. So it's not that alkali-activated cements are worse than anything else we're using, actually performing equally to the modern blended Portland cements and concretes that we use in modern infrastructure. However, we identified that there were no studies on carbonation of sodium sulfate activated slag cements, at least to the best of our knowledge. So we decided to pursue this study. So for these systems, we adopted a CO2 concentration of just 1%, because previous studies have shown us that if we increase the CO2 concentration to induce accelerated carbonation beyond 1%, the reaction products that we form do not match what we identified when we test the materials on the natural carbonation conditions. So if we have a look at this, these materials actually carbonate really quickly under accelerated carbonation conditions. It's interesting also to see that it doesn't seem to be like a trend in the carbonation of these type of materials. For example, here we have different aluminum or magnesium content. It doesn't seem to be a trend very clearly about that. But what was really interesting for us was because we couldn't find much information about the potential carbonation of these cements. We have done experiments under accelerated carbonation conditions, but also under natural carbonation conditions. And you can see here in these photographs, the tremendous difference in the carbonation front that is developed depending on the conditions used to induce carbonation. So under accelerated carbonation conditions, we see a lot of microcracks in the system. We see a lot of oxidation near the microcracks in the photographs, and we see a very uneven carbonation front. When we do carbonation, the natural carbonation conditions, 2 or 3 major observations are: one is when we apply the phenolphthalein pH indicator in the carbonation region, or that we assume is carbonated because it's like this light gray ring that is mostly oxidation of the sulfides present in the slag. We still see a pink color, which means that the material is holding a pH above 9, even in the area where we think that carbonation is actually happening. Conversely to what we see in the accelerated carbonation ones, we clearly see a colorless area around this shape of purple, where we know that the pH is above 9. The other thing we identify when we do natural carbonation is, yes, we still see microcracks, but we cannot see as many as we see under accelerated carbonation conditions. So still is a lot of work to do for us to elucidate what is actually happening in the systems. But what is really clear to us is that using or inducing accelerated carbonation sodium sulfate activated cements might not give us a very realistic picture of the performance of these materials, and certainly is not replicating the reactions that are actually happening in these materials on the under natural carbonation conditions. So these open, I will say, more questions than giving us answers, because we need to determine how best we could predict the performance in terms of carbonation of these materials in the longer term. Clearly, accelerated carbonation might not be the way to do so. So some general remarks for me is that sodium sulfate is a suitable activator to produce alkali-activated cements. I hope I produced and presented sufficient evidence for you to see that it can work, but it will not work in every case. We need to find the right activator for the right slag chemistry. Also, there is a strong correlation between the slag chemistry and the kinetics of reaction. So I will say a lot of research is stopped because the materials do not harden as quickly as we might want them to harden. But if we look at the longer term performance, the degrees of reactions and mechanical strengths developed by these materials are very comparable. So we really need to focus our efforts in controlling that kinetics of reaction if we would like to use these materials in the future. Also, in the case of sodium sulfate activated cements, is evident that different types of reaction products will form depending on the magnesium oxide, aluminum oxide ratios in the slag. Far more research needs to be done to understand in which ranges composition some of the secondary reaction products will form, because we know that a lot of the durability, performance, and also compressive strength performance of these materials strongly dependent on these secondary reaction products. So more research is needed. And well, there are many unanswered questions about this type of cements. So yeah, it's a lot of work to be done, but it's worthwhile to continue exploring. So of course, this is not just my work, it's a team effort. And I would like to thank in particular my colleague Shinran Ki, because well, the two of us developed a lot of the early work in this area. Zhengliang Yue, he is a current PhD student working on these systems, doing a fantastic job evaluating a carbonation potential of sodium sulfate activated slag cements. Kate Button, she was a master student who initiated all the work on the effect of limestone replacement in this type of cements. Alistair Marsh, Yuvaraj Dandapani, Samuel Aduamankwa, and John Provis, and my colleagues who had been driving also all the research in these areas and other areas of alkali-activated materials over the years. So of course, also I would like to thank our funders because without them, we could have not performed this research. So that's all from me. Thank you very much for your attention. I'm happy to answer any questions you might have.